my success. Thanks, Tim. So obviously we're swapping around time, so it's nice to see that the process here is robust enough to cope with this uncertainty. Some contributors to this presentation, none of whom you'll know apart from Clements. So what I want to talk about is, first of all, some general variability considerations in crash, then look at the numerical noise side of things, numerical robustness, numerical noise, and then some physical noise considerations, with a summary then at the end. So, variability. Our process is fully virtual. So what this means is we do all our design based in the virtual world, and we test prototypes only after we've released £300 worth of tooling or something like that. We have, as I said, one validation test after we've done this, and no test repeats. So we've got no idea actually of the variability in the product once we're testing it. We've got to get no surprises at test. That has to be the fundamental thing that we're trying to get. These surprises lead to, and we all know these, late design modification, inefficient design. So if I base my design on certain assumptions, if my assumptions are wrong, I will have necessarily an inefficient design. I only do one test, my validation test. So it may be that if I do a second test, it might be a failure. My first test is a pass. If I get that test done by a legislating body and they find there's a failure, I've got a really big issue, because that might be a recall of vehicles. This could be millions of pounds to the company. So it's all very costly, which is what it's about. It's about cost, as far as we're concerned. Variability leads to these surprises because of all the things that we know. So test-to-test variation. You spoke about initial assumptions being different, being wrong because of the variability. And non-robust numerical models, which is where we're coming from with Clements' talk. So in my world, in Crash CAE, I've got to think about two things. First of all, the response of the design to the physical properties and environment variabilities, represented, of course, in my model. So I've only got my model to talk about the physical world. And also the numerical noise, which is often has no physical meaning, it's purely numerical effect. And the CAE is a very useful tool for all of these, but it brings its own problems. So, numerical robustness. This curve shows 30 runs. The only difference between them is numerical noise. So it's a question of how I arrange the input. There's no difference in the input deck as such. It's purely about how I arrange it, how I organise it. And that's quite scary. So this is a crash result. Each of these is one of these runs. This comes from, in crash terms, something like 5 million degrees of freedom, 100,000 or 80,000 time steps. There's just so much opportunity there for rounding errors and issues like that to build up. Each of these runs, though, is valid. As I say, I only changed the organisation of what went into the runs. They're all exactly nominally the same input. And the nominal, or the one that I started with, is not necessarily any sort of average here. It's simply one of the one randomly chosen option from that population. If I then pretend that I can approximate the maximum of these curves by distribution, that's the distribution of these curves. So I'm taking a slice, if you like, through there, and that's the distribution of it. Again, forget the idea that it's a normal distribution. It's purely an illustration of the sort of distribution. We then did a change to the design, and this was the distribution that we got to that design. So the question is, how different are those two designs? 30 runs were done, so it represents 30 runs in each case. If I take the mean of those populations to be a measure of the difference between these two designs, then the difference, the change that I've affected is 4.6. The two runs that I originally did, so from the original 30 runs that I showed, I originally just had one run, and I did a back-to-back run with the new design. And that's where they came out. Coincidentally, if you like, arbitrarily, 1 point there, 1 point there. So I originally thought my design change was 3.8 rather than 4.6. So you could say, well, I've actually done better than I thought I did. But potentially I've over-engineered the design. I've over-engineered it on the basis that my change was 3.8. Actually, I've got a bigger change. I've got 4.6. If I was to say, well, what could have happened out of a back-to-back? I could quite easily have got a run here relating to this one, and a run here, if I'd chosen any two runs. So I could have quantified the benefits 2.8, or I could have quantified it as 6. So if I happen to get this run and this run in a simple back-to-back comparison, I could have got 6. So I could arbitrarily get anything between 2.8 and 6. I happened to get 3.8. The mean said it was 4.4. So it's chaos really as far as that's concerned. So if you look at what is actually significant, there's this idea of model precision. So this original model here, within some limits, has got a model precision of 4.4. If I get a run, then do another run, if the difference between them is greater than 4.4, I can say there's a change in design. If it's less than 4.4, I can't. That's the level of precision of the model. In this case, clearly I've got a model that's more precise. So I need to get a run that's outside of these limits to be able to call that run different to that population. Clearly in this case, for some reason, the new design is more precise than was the old one. And that perhaps just reflects the fact that the design is a better design. So the upshot of that is that a back-to-back comparison is effectively invalid if you don't know anything more about it. The variation can be bigger than design change, and actually often is. We're often making decisions based on an assumed design change that's smaller than the variability I've got numerically. I can't do that sort of robustness study for everything. I haven't got the CPU study, so I've got to be able to deal with that. And the way to do that is to understand the precision. Unless I understand the precision, I don't know the significance of any design change. And the other thing is apparently repeatable results. So some software programs, particularly in Crash, will say, I'll give you the same result every time I run. Now that is invalid because that's purely putting an artificial constraint on saying I'm always going to do it in the same order. Doesn't mean to say the variability is gone. It's just an artificial way of forcing one result. So thinking about sources, and this is the link with Clements's work. We've recently started to employ some of the principles that we're talking about there. So where does the numerical noise come from? And it can be very difficult to trace. In the Crash world, we often only see it actually later on. So this is something like 120 milliseconds. It's very late on in the Crash event, and we notice these two differences. So here's two design conditions. No, I beg your pardon. Two nominally identical runs. So I've done the same again. I've just run the model twice, and got these two differences. This contour represents the degree of variability. So as Clement showed before, what this says is we've got a lot of variability here, a lot here, not much variability here. So this red represents the difference between these two models. So what I'm trying to do is to see, well, where's that coming from in numerical terms? And this was a joint project then that we did with SEAI, with Clements, using these principles. Splitting it down into the modes, as he explained, we identified 4 modes which were principally responsible for the variation. And you can see what they look like. So there's a mode doing this difference. There's a mode representing this difference, and this difference. And this again at state 50, which is probably 50 milliseconds or something. So the question is, where does that come from? If we trace those modes back now to state 13, which is 13 or 15 milliseconds, again they're the same modes. So what is initiating, or what is the earlier effect of each of those modes, is these 1, 2, 3, 4, 5 number. So they equate to the same modes. So in other words, mode 1 here ultimately leads to mode 1 afterwards. And doing a bit more analysis showed that taking the first mode and looking at what is the real difference inside, these are two hoops inside an airbag. So they're hoops that represent bits of tethers, as we call them, inside the airbag. And in one case we had a contact issue here, and in the other case we had no contact issue. And bearing in mind these are nominally identical runs still, this is just a measure of the uncertainty, the numerical noise in the system. So what we did, the question was asked, the solution to this was to make the model more robust, more certain, less variable, by modifying the contact definition there. So that this difference in contact here didn't happen, it was a robust contact definition. So the point is that to improve the precision in this case, we've got to have a stable model, we've got to have models that don't react in that way. We can use this idea of tracking the variability to improve the model. And that can often reduce the variability. And scatter can be physically meaningful. So in this case it's a numerical thing, but sometimes if it is about dropping the ball on the sharp edge and it goes one way or the other, that's a physically meaningful concept that's brought out by this numerical thing. So it can reflect a physically meaningful variability. So an example of physical noise, that's all numerical. This is some results which I have shown in the past, so I don't want to go into great detail. But in my world of crash simulation, this is a crash dummy, and to certify the crash dummy, we have a test like this where this great big log is flown into the dummy, and the dummy parameters have to fit in with within certain limits. So this is it all in the physical world. The dummy has to fit in within this box. This is a speed constraint, and this is a deflection constraint. Each of these dummies, each of these dots represent a dummy, each of those is a valid dummy, again in physical world. And there's about 15% difference in the dummy stiffness. So to me the question is, what does that mean in my vehicle world? So what we did was to take a CA model of the dummy and parameterized it. So for each of these components we put in variables. Variables that reflected material stiffness parameters. This is a copy of the last slide, so these are physical dummies, each of these being valid, fitting within the box. Through a Latin hypercube, again, variation of the parameters, the input parameters, we created a set of CAE dummies. And these ones here correspond then to acceptable dummies in the box. So each of these dummies, these CAE dummies, is valid. Taking that set of valid CA dummies, we put them through a crash model and obtained some crash results. So again, each of these red dots now corresponds to an acceptable dummy. This gives me real results, or real virtual results, if you like, out of the crash model, and shows me what my range of results are. So again, turning it around into a probability. This is my dummy measurable. This is an indication of the distribution. Here's my nominal dummy. So what that says is that 75% of different dummies I could expect to be a pass. 25%, thereabouts, I could expect to be a fail. Now I have to decide whether that's good enough, whether 25% over my original result is acceptable. But at least I've got the data to do it. So, summary. Variability leads to test surprises and cost. That's what I'm interested in, is the cost that's associated with these surprises. It's got to consider physical and numerical. I've got to consider both of those, and it's got to be a consistent process. It's got to be a continuous process as far as our development is concerned. We're looking at that in a structured way. It's got to be structured, and it's got to be based in or baked into the vehicle development program, and not just seen as an added extra. And often it's difficult to persuade our development programs, development managers, that we've got to do this. It's seen often as an extra or a nice to have, and so it always falls off the table. And there are hardware and software developments. As hardware gets quicker, cheaper maybe, and the software progresses, we're starting to be able to support these in a much more structured way. And that's that.